Greetings from Denmark. I'm Jason Box. I'm a professor in glaciology and climate at the Geological Survey of Denmark and Greenland. I wish that I could be there in person with you to discuss the many climate issues at COP29. I'll be sharing the Arctic Monitoring and Assessment Program's most recent compilation of climate indicators, climate issues of concern for the Arctic. A collection of multiple climate indicators based on measurements and Greenland ice sheet tipping point. The content here is from an international constellation of experts, part of the Arctic Monitoring and Assessment Program's Climate Expert Group. Arctic Monitoring and Assessment Program produces IPCC-like reports focused on the Arctic. Find the reports at amap.no. Let's start with the map of Arctic temperature change. As you can see, it's an overall warming pattern, with most warming where the sea ice decline has been the greatest. You have the North Atlantic warm current here terminating, so a really highly dynamic area of sea ice decline, where at this hotspot you have 7 times warming as compared to the global average. Greenland ice sheet has been warming at about 1.7 times the global average. I'll be talking more about that later in the context of Greenland's tipping point. A main product is this super graphic where we compile a bunch of observational records starting with Arctic air temperature. This is from 1971 forward. And what you have with Arctic air temperature is a jump up in 2005 associated with an abrupt increase in winter warm events. That's a key contributor to this Arctic warming much faster than the globe here in the black curve. Greenland ice sheet temperature at 10 meters depth, the blue curve, shows the warming of the surface snow cover of the ice sheet by 2 Celsius over this period. Arctic precipitation, it's an overall wetter Arctic pattern. I'll talk more about that later. Arctic river discharge, an overall increase in Arctic river discharge, 13%. As you can see, most of the river discharge is from the Eurasian Arctic, with North American Arctic rivers also increasing their discharge. This is important for a freshening of the Arctic Ocean. The Arctic Ocean is only 1% of global ocean volume, but receives 5% of river discharge. So the Arctic Ocean is freshening, also in part because of sea ice melting. Arctic tundra getting greener from satellite records. This pattern is predicted well by air temperature and precipitation variations. We have a longer growing season, effectively, of Arctic vegetation, accompanied by a so-called shrubification of the Arctic. Fire, very sporadic, but we have record-setting fire here in 2020. The conditions for fire have increased, mainly driven by lightning ignition. You have more cloud development, and along with clouds you get lightning driven by warming. Snow cover decrease. This is several months before the Arctic sea ice decrease. Profound transformation of the landscape when snow cover is lost. The land ice changes here expressed in mass changes. So you have the mass of all Arctic land ice producing a sea level rise that I'll talk about more later. One metric to illustrate the air temperature increase is the area of the Arctic experiencing temperature above 0 Celsius, the melting point. And as you can see, that really becomes obvious trend after about the year 2000. And if you remember back to the 1990s, even the early 2000s, it was impossible to really see the Arctic climate change signal. But now that signal has really punched out of the noise. The changes in precipitation, rainfall, snowfall, you have Again, a wetter Arctic, increasing rainfall, these green colors, decreasing snowfall, really because the snow is converted into rain. The Greenland ice sheet is cold enough for this increase in atmospheric humidity and moisture transport to deliver an increasing snowfall, and that helps buffer the Greenland ice sheet from warming. The fact that the Greenland ice sheet is taking on about 15% more snow in the last 200 years. It's a modest increase in snowfall, but it helps maintain the ice sheet. Greenland sea level contribution is roughly twice that of Antarctica. Alaska is almost as much of a sea level contributor as Antarctica. This is really impressive because the Antarctic ice sheet is 10 times the volume of the Greenland ice sheet. Yet, Greenland is the largest single regional source of global sea level rise. So the Arctic is a hotspot for land ice loss. So I'll spend the rest of the time getting into the tipping elements of the Greenland ice sheet. And conceptually, you have time 1, time 2. So this is going forward in time, and what you have is a dynamic drawdown of the ice sheet into a warmer part of the atmosphere. The atmosphere is warmer down here. There's basically more greenhouse effect down here than up here at the high and dry elevations of the ice sheet. This thinning into a warming part of the atmosphere produces a nonlinear increase in the melt area across the ice sheet. This nonlinearity is represented by this diagram where you have temperature change on the horizontal. So you have warming in this direction, and the ice sheet remains stable and temperatures are fluctuating back and forth and edging closer to this critical temperature, this threshold viability of the ice sheet. And once the temperature goes above that, it's possible to tip into an unstable regime of loss. Now, the real point here is how much time is spent above this critical threshold. The roadrunner and the coyote. The roadrunner can go off the cliff and run back on. So you can have a warm year that shatters temperature records, yet a cold year following that keeps the ice sheet stable. So this graphic illustrates this concept of the time spent above the warming threshold. If you push the ice sheet, say, to 4 degrees Celsius above its threshold, then the time to lose some significant fraction of the ice sheet drops down. We're kind of around here with warming of almost 2 Celsius above pre-industrial for the Greenland ice sheet. So if temperatures continue rising, then you more rapidly get into this steeper part of the curve. Conservatively, we may be, say, here. So you can see that we're at a point where the warming can bring us into a dramatically more impactful effect on the volume of the ice sheet. This graphic illustrates the same thing where here you are with a high volume of the ice sheet. Here's your temperature change. So here we are in the present climate. And as long as we're up here, the volume of the ice sheet remains high. However, if we pass over this tipping point, then you can have an abrupt volume loss, and even cooling will not bring you back to this high volume. You need to get a much colder condition to then regrow the ice sheet to a high volume. This is the fluctuations today. This is what warming will produce, the tipping, a collapse of the ice sheet. This can take hundreds, thousands of years to occur. And to regrow the ice sheet, you have to cool and stay cold for long enough for the ice sheet to regrow. And with that, I wish you a powerful COP29 where you can get the message out of your science and have that influence policy so that policymakers can do their part of the job to address this enormous challenge that we face with anthropogenic climate change.